So here we want to find an equation of the tangent line to a curve at a given point. So in the previous video we simply used the slope of the secant line, and which we find between 2 points, and bring it closer and closer to a single point, and we reduce the slope of the secant line to the slope of a tangent line at a single point, because a tangent line touches the curve exactly at 1 point, whereas the secant line touches a curve at 2 points. So we can take that approach, but now that we have a difference quotient from earlier, so the formula for difference quotient is right here, and we're going to make use of the difference quotient to find the slope of the tangent line. So how does this work? Now we have x and x plus h, and if I took the limit h approaching 0, then the point on the right hand side, x2, as h becomes smaller and smaller, it's going to move closer and closer toward x. It is the same concept where we narrowed the slope of the secant line and to a single point we're going to move the value of h closer and closer to 0, which would bring the point x2 closer to x1, reducing the slope of the secant line to the slope of the tangent line. So instead of doing that computational approach, we're just going to make use of the difference quotient to find that value, which is the slope of the tangent line. So how do we go about doing that? The very first step is to use the difference quotient. I'll just write it as dq. It's given by that formula. Now keep in mind, you can't simply plug in this formula and apply the limits directly. You would get 0 over 0, you would get an indeterminate form. So be very careful, we have to do some algebra here. So I'm going to start with f of x plus h, so I'm going to replace the x there by x plus h. Make sure you put the parentheses properly, so 4 times x plus h minus 3 times x plus h squared. That is the f of x plus h part, minus 4x minus 3x squared. That is the f of x part. So that is f of x plus h minus f of x, and divide by h. So we have 4x plus 4h minus 3 times FOIL x squared plus 2xh plus h squared. Distribute the negative, minus 4x plus 3x squared divided by h. So I can get rid of the 4x term, and that would leave me with limit h approaching 0, 4h minus 3x squared minus 6xh minus 3h squared plus 3x squared divided by h. So those two terms would go away, leaving us with limit h approaching 0, 4h minus 6xh minus 3h squared. So So what do we have in common in the numerator? We have a h in common, so limit h approaches 0, 4 minus 6x minus 3h squared divided by h. All I did is I pulled the h out, so that would be 3h. Cancel the h. And now we could simply apply the limit. The first term doesn't have h in it, so it will remain as is. The second term doesn't have h in it, so it remains as is. The third term has h in it, so when we apply the limit, it goes away. 3 times 0 is 0, so we end up getting 4 minus 6x. That is the limit h approaching 0 of the difference quotient of f of x. And that is simply the slope of the tangent line. So the given point is 2, minus 4. So we have a point, and at that point we can find the slope of this function. So all we have to do is find m. So how do we find m? We have the slope expressed in terms of 4 minus 6x, because that is the slope of the tangent line. And if we plugged in 2 in that equation, y equals 4x minus 3x squared. We have 8 minus 12, which is negative 4. So this point is simply the point where we're trying to find the equation of the tangent line. So I have an x coordinate there, which is x. So plug in x is equal to 2 in the slope of the tangent line that we derived. So m would simply be equal to 4 minus 6 times 2, which is 4 minus 12. We get minus 8. So if I represent it in point slope form, the point x1, y1 is 2 and negative 4. So y minus y1 is equal to m times x minus x1. So the equation of the tangent line in point slope form is y plus 4 equals negative 8 times x minus 2. So that is the final answer. If you want, you can write it in the slope-intercept form with a little bit of algebraic operations. So here we have y equals square root of x, and we have 1, 1. Let's do the same thing. Limit h approaches 0. The difference quotient. So limit h approaches 0. F of x plus h minus f of x divided by h would simply be the slope of the tangent line. So we have the point already. If we find the slope, then we can put it in the point slope form, and if we can put it in the point slope form, we could write it in the slope intercept form. So let's see. Limit h approaches 0, square root of x plus h minus square root of x divided by h. Now, in the previous video, I did a couple of examples where if you apply the limit directly to this particular difference quotient, you will get 0 over 0, which is an indeterminate form, and obviously that is not the correct answer. So what should we do? We have to rationalize the numerator. So we multiply and divide by the conjugate. The conjugate of the numerator, square root of x plus h minus square root of x, is square root of x plus h plus square root of x. So if I follow the numerator by multiplying that term with that term, we will have square root of x plus h squared minus square root of x squared divided by h times square root of x plus h plus square root of x. The root and the square would get cancelled, and we would simply have limit h approaches 0, x plus h minus x divided by h times square root of x plus h plus square root of x. The x's would go away, and we'd simply have limit h approaches 0, h divided by h times square root of x plus h plus square root of x. Now the h goes away there, and we'll simply have 1 over square root of x plus h plus square root of x. When we apply the limit, the first term would become square root of x in the denominator, the second term would also be square root of x, and if I combine the two, I'd simply have 1 over 2 root x, and that simply is the slope of the tangent line in terms of x, which we obtain using the difference quotient. All I have to do is now plug in the point that we have in the problem, that is the correct point corresponding to the function. So if I use that point in the slope of the tangent line, I'll have m equals 1 over 2 times square root of 1, which is 1/2. So I have the slope of the tangent line at 1, 1. And I know the point where I'm looking for the tangent line, which is 1, 1. So if I put it in point slope form, I have y minus 1 equals 1/2 the slope, x minus 1. So that would be the point slope form. Let me just go ahead and convert it to the slope intercept form. So we have y minus 1 equals 1/2 x minus 1/2. Move the 1 to the other side, so y would equal to 1/2 x minus 1/2 plus 1. So y would equal to 1/2 x plus 1/2. And that is the equation of the tangent line at 1, 1 for the function y equals square root of x. So we did difference quotient already, and we found the slope of the tangent line using the difference quotient, which is the benefit of having the difference quotient. Now we're going to do 2 simple examples on difference quotients. There is an interesting behavior that you should have noticed already. If not, in these examples I would mention what that behavior is when we find the difference quotient. So the difference quotient is simply f of x plus h minus f of x divided by h. The function is x squared minus 4, so x plus h squared minus 4 minus x squared minus 4 divided by h. If I FOIL, I have x squared plus 2xh plus h squared minus 4 minus x squared minus 4. I'm leaving it as is for a reason. Now I'm going to go to the FOIL version and I'm going to move that term and that term close to each other and write it this way: x squared minus 4 plus 2xh plus h squared minus x squared minus 4 divided by h. And those two terms will get cancelled, and you'd have 2xh plus h squared divided by h. We have the h in common in the numerator, so h times 2x plus h divided by h. The h's would go away. We simply have 2x plus h. Something interesting happened if you observe carefully. Excuse me. F of x is x squared minus 4. And when we found the difference quotient, that x squared minus 4 got cancelled. So it just went away. So if we do everything properly, the original function will disappear when we find the difference quotient. That is a key thing to notice. And we saw it in the previous one. Square root of x disappeared. And here 4x minus 3x squared disappeared. So if we did the algebra correctly, the original function x squared minus 4 will disappear when we find the difference quotient. So the last step, or the last problem, is f of x equals 1 over x plus 1. So the difference quotient is f of x plus h minus f of x divided by h, which is 1 over x plus h plus 1 minus 1 over x plus 1 divided by h. We need to get a common denominator if we have to combine those two together. So the common denominator between x plus h plus 1 and x plus 1 is the product of the two. So I'm going to multiply and divide by x plus 1. And over here, I'm going to multiply and divide by x plus h plus 1. And divide that by h. So now I have a common denominator. So I have x plus 1 minus x plus h plus 1 divided by x plus 1 times x plus h plus 1 divided by h. If you flip and multiply, we'd simply have x plus 1 minus x plus h plus 1 divided by h times x plus 1 times x plus h plus 1. Distribute in the numerator x plus 1 minus x minus h minus 1 divided by h times x plus 1 times x plus h plus 1. The x's would go away, the 1's would go away. We have negative h over h times x plus 1 times x plus h plus 1. The h's would go away. We simply have minus 1 over x plus 1 times x plus h plus 1. Now, just in the last problem I mentioned that if you did everything properly, the original function is going to disappear and things would just fall in place. But in this problem, it didn't seem like it. 1 over x plus 1 just didn't disappear. It's not obvious. And in the square root of x problem over here, it wasn't obvious. The algebra that we did somehow worked out, and we ended up getting the answer. So typically with algebraic functions or polynomial functions, such as the quadratic, the linear function, a cubic polynomial function, all of those, when you find the difference quotient, the original function would just disappear. So x squared minus 4 here is a second degree polynomial. It is a quadratic function. It is going to disappear. But 1 over x plus 1 is not. It is a rational function, and which is why it is not quite obvious. But if we did some bit of algebra in other ways, perhaps it would become obvious, but we don't have to get into that. So anytime you have a radical function or a rational function, it won't be obvious. The original function, even though it is going to disappear, it is just not going to be obvious. But with polynomial functions, such as x squared minus 4, when you find the difference quotient, the original function will always disappear. So we've got to know when a derivative will exist. So typically, as a golden rule of thumb, if you have a continuous function, then we don't have a problem. We will have a derivative. Everything is peachy. But if there are discontinuities, then the point where we have a discontinuity will not have a derivative. This goes back to limits. If we have limits, and if there are discontinuities, a limit doesn't exist at the discontinuity, because the right-sided limit will not match the left-sided limit. So a good example would be the jump here. If I say that is 1 and that is 2, the right-sided limit toward 2 is 2, and the left-sided limit is 1. And they don't match. If the limits don't match, if the one-sided limits don't match, then the limit doesn't exist. And if the limit doesn't exist, then the derivative cannot exist. The reason being, the derivative is directly related to the limit at a given point. So discontinuities are quite important when we try to find the derivative of a function. So how do we find the derivative of f of x is equal to 3x minus 8? 3x minus 8 is a line, so it is of the form mx plus b, and we know the slope of a line is simply m, and in this problem it is 3. So if we have a line, so the y-intercept here is negative 8, we'll arbitrarily say that that is y equals 3x minus 8. No matter what point I pick on this line, the slope will be the same. So if I drew a tangent line here, no matter what point I pick, the slope is going to be the same. So slope of the tangent line would simply be 3. So which is negative infinity to infinity. So, in other words, the derivative is 3, 4,
every point in negative infinity to infinity. That is the domain of the derivative also. Now how do we verify this? We know the derivative f prime of x is simply limit h approaches 0 f of x plus h minus f of x divided by h. So limit h approaches 0, the function is 3x minus 8, so I'm going to replace x by x plus h minus 8 minus the function 3x minus 8 divided by h. So if I distribute, I would have 3x plus 3h minus 8 minus 3x minus 8 divided by h. I'm going to move things around here so things become clear. I'm going to write this as 3x minus 8 plus 3h minus 3x minus 8. That term and that term are one and the same, so they all get cancelled. And we have limit h approaches 0, 3h over h. The h's go away, and limit h approaches 0, we get 3. And there is no h in that limit, so the answer would simply be 3. So as I suggested at the very beginning of this problem, that the limit of this the derivative of this function would be 3 in the domain of the function, and it turns out that f prime of x, which is the derivative, is 3 no matter what value of x I pick in negative infinity to positive infinity. So the derivative is 3. So what we're trying to say here is the slope of the tangent line at any given point on this function is 3. So the derivative is 3, the slope of the tangent line at any point of this function is 3. So the derivative of this function 3x minus 8 at every point in the domain of the function 3x minus 8 is 3. Now here is another example where we have f of t equals 1 over square root of t. So first thing we have to do is the domain of f of t. We cannot plug in 0. If we plug in 0, the denominator would become 0, and 1 over 0 is undefined, so the domain has to be negative infinity to 0, union 0 to infinity. So this is an infinite discontinuity at x is equal, t equals 0. Damn it. At t equals 0. Let's find the derivative f prime of t. Now you've got to keep in mind, when we take the derivative, we always take the derivative of the function f with respect to its independent variable. So that is the derivative of f of t with respect to t. And what is t here? T is the independent variable. So how do we find this? We're going to make use of the difference quotient, f of t plus h minus f of t divided by h. So limit h approaches 0, f of t plus h is simply 1 over square root of t plus h minus 1 over square root of t divided by h. So we need to get a common denominator so we can combine the numerators together. So the common denominator is square root of t times square root of t plus h. So I'm going to multiply and divide by square root of t there. I'm going to multiply and divide by square root of t plus h there. And divide the entire thing by h. So we have a common denominator, so we can combine the numerators and write it as square root of t minus square root of t plus h divided by square root of t times square root of t plus h over h. Now if we flip and multiply, we end up having square root of t minus square root of t plus h divided by h times square root of t times square root of t plus h. And you can't simply apply the limit here, because if we did, we're going to get 0 over 0. And this is where rationalizing the numerator comes into play. So limit h approaches 0, I'm going to multiply and divide by the conjugate of the numerator, and I'm going to combine the two roots, and the numerator, if we FOIL, would end up becoming square root of t squared minus square root of t plus h squared, and we divide that by h times square root of t times t plus h times square root of t plus square root of t plus h. The root and the square will get cancelled, and we would simply have t minus t plus h divided by h times square root of t times t plus h multiplied by square root of t plus square root of t plus h. Distribute the negative, we have t minus h divided by h times square root of t times t plus h times square root of t plus square root of t plus h. So the t's will get cancelled. We'll have limit h approaches 0, negative h over h times square root of t times t plus h times square root of t plus square root of t plus h. The h's will go away. We'll simply have limit h approaches 0, 1 over square root of t times t plus h times square root of t plus square root of t plus h. And there is a negative in the numerator. When I apply the limit, I have negative 1 over square root of t times t plus 0 times square root of t plus square root of t plus 0, which is negative 1 divided by square root of t times t multiplied by square root of t plus square root of t. That would equal to negative 1 divided by square root of t squared times 2 square root of t. So that would be minus 1 divided by t times 2 root t. So the answer is negative 1 divided by 2 times t root t. We can also write this as negative 1 divided by 2 t times t raised 1 over 2, and we can combine the exponents and write it that way. And the domain here, since the function has a discontinuity at t equals 0, the derivative will also have a discontinuity at t equals 0. In other words, we cannot plug in 0, in the derivative, because if we plug in a 0 here in the denominator, it is going to result in a divide by 0. So the domain of the derivative is also negative infinity to 0 union 0 to infinity. So here is another function, and we want to find the derivative of this function. So the domain here is negative infinity to positive infinity. The reason being, I can plug in any number in the denominator or the numerator, and I'm going to get a well-defined real number. So how do we find the derivative of x? The derivative, or f of x, is simply df over dx. That is the same as saying dy over dx if I call y is equal to f of x. And that is equal to the limit of h approaches 0, f of x plus h minus f of x divided by h. So in our case, that would be x plus h divided by x plus h squared plus 2 minus x over x squared plus 2 divided by h. And we need a common denominator, just like we required that in the previous problem. So I'm going to multiply the first fraction by x squared plus 2 and divide, and multiply and divide the second fraction by x plus h squared plus 2 and divide the entire thing by h. So you can see why using the difference quotient could get really troublesome anytime we want to find the derivative. Things are getting really complicated here. So we have x plus h squared times x squared plus 2, and the numerator is x plus h times x squared plus 2 minus x times x plus h squared plus 2. I am going to expand and simplify. So I have x cubed plus 2x plus x squared h plus 2h minus x times expand x plus h squared, FOIL, I'll get x squared plus 2xh plus h squared, and I have a 2. And divide the entire thing by h times x plus h squared plus 2 times x squared plus 2. Distribute the x in the second term. We have x cubed plus 2x plus x squared h plus 2h minus x cubed minus 2xh minus xh squared minus 2x divided by h times x plus h squared plus 2 times x squared plus 2. The x cubes will go away, the 2x will go away, and I simply have x squared h plus 2h minus 2xh minus xh squared divided by h times x plus h squared plus 2 times x squared plus 2. There is a h in common in the numerator, so let me switch colors here so you can see things better. H approaches 0, pull the h out, I have x squared plus 2 minus 2x minus x h, and divide that by h times x plus h squared plus 2 times x squared plus 2. The h's would go away. Limit h approaches 0. We have x squared plus 2 minus 2x minus xh divided by x plus h squared plus 2 times x squared plus 2. If we apply the limit, the numerator would simply be x squared plus 2 minus 2x plus 0 divided by x squared plus 2 times x squared plus 2. So the derivative here is x squared minus 2x plus 2 divided by x squared plus 2 squared. And this derivative would exist on the entire domain of the function because there aren't any discontinuities. So that is how we find the derivative here. Off to the next problem. Here we want to find the derivative of g of t with respect to the independent variable, which is t. So dg over dt, or g prime of t. And in this problem, the domain cannot include the value 3, because if I put 3 in that function, the denominator would be equal to 0. We will have an infinite discontinuity. So I'll make note of that in a second. So limit of the difference quotient, and the domain of the function is negative infinity up to 3 union 3 to infinity. There is an infinite discontinuity at t equals 3. So we have limit t approaches 0, 1 minus 2 times t plus h divided by 3 minus t plus h minus 1 minus 2t divided by 3 minus t, entire thing divided by h. We need a common denominator. So I'm going to multiply and divide the first fraction by 3 minus t. And I'm going to multiply and divide the second fraction by 3 minus t plus h. and divide the entire thing by h. We have a common denominator, so we can combine the numerators. So we have 1 minus 2 times t plus h times 3 minus t minus 1 minus 2t times 3 minus t plus h divided by the common denominator, which is 3 minus t plus h times 3 minus t, and the entire thing will be divided by h. So if we flip and multiply, that would reduce to limit t approaches 0, 1 minus 2 times t plus h times 3 minus t minus 1 minus 2t times 3 minus t plus h divided by h times 3 minus t plus h times 3 minus t. Distribute and simplify. Oh, I made a mistake. It is not t approaches 0. I am sorry. It has to be h approaches 0. It was not blatant. I didn't think twice there. So let's FOIL this. So we have 3 minus t minus 2 times t plus h times 3 minus t minus 1 minus 2t times 3 plus 1 minus 2t times t plus h divided by h times 3 minus t plus h times 3 minus t. So that would equal to limit h approaches 0, 3 minus t minus 2t, minus 2, I'm going to FOIL those two. I'll have 3t plus 3h minus t squared minus th minus 3 plus 6t plus t plus h minus 2t squared minus 2th divided by h times 3 minus t plus h times 3 minus t. You can see how complicated this is becoming. Should have used smaller fonts, I guess. So the numerator would become 3 minus t minus 6t minus 6h minus or plus 2t squared plus 2th minus 3 plus 6t plus t plus h minus 2t squared minus 2th divided by the entire thing, h 3 minus t plus h times 3 minus t. So the 3's will get cancelled, the 6t's would get cancelled, the t would get cancelled, the 2th would get cancelled, the 2t squared would get cancelled, and we are simply left with limit h approaches 0, negative 6h plus h, that's negative 5h, over h times 3 minus t plus h times 3 minus t. The h's would go away, and if we apply the limit, the answer would be negative 5 divided by 3 divided by 3 minus t squared. Since the function has a discontinuity at t equals to 3, the derivative would also have a discontinuity at t equals 3. So the derivative has the domain negative infinity to 3 union 3 to infinity. So we can see how using the difference quotient to find the derivative could get out of hand really fast. So we have to find better ways, and eventually when we get to chapter 3 we'll see that things could get simpler by using rules of differentiation. But the key to remember here is the derivative of a function would be equal to the slope of the tangent line at every single point of the function, and if there is a discontinuity then the derivative cannot exist at that discontinuity. Also, if there is a sharp turn or a cusp of that sort, the derivative will not exist at that particular point.